So this is the flow sheet where we build our model using the elements or nodes or fittings available to us from the component toolbar across the top here. Okay, so we've got our pipes tab, so we've got different pipe materials, steel, stainless steel, and so on. We've got our boundaries, so we might know, for instance, the pressure, we might know the flow rate of the system, we might have a tank, this is an open pipe, an exit point in the system, sprinkler nodes, and so on. We've got our various junctions, so bends and miter bends, T-junctions, and connectors. The connector node allows you to have as many pipe connections at a single point in a network as required. So you've got centrifugal pumps, PD pumps, all your various valve types, gate valves, plug valves, butterfly valves, and so on. Pressure and flow control devices, differential pressure controllers, check valves, general resistances, so KV, KF nodes, and so on. Orifice plates, reducers, relief valves, bursting discs, and heat exchangers. Okay. So what I'll do is actually to demonstrate the user interface and how we go about manipulating and developing models is I'll just create a very simple cooling water circuit, okay? And I tend to always begin my models by placing boundaries on the flow sheet firstly and then creating the connectivity. So I know the overall connectivity of this particular model, okay? And it's going to be something like this. I'm going to have 4 heat exchangers along each of these branch connections. So 1, 2, 3, and a 4th branch connection. Now you can see when I develop the model this way, the software automatically fits a bend and a T-junction in the appropriate location. I can rotate nodes by selecting Control and the letter R, or right mouse click and rotate node. Okay, I'll just do Control R once again. Just tidies it up a little bit. You'll see as well a little red dot at the T-junction, and that denotes the branch pipe connection. And there's a little explanation as to what that means for T-junctions and for Y-junctions. Okay, so the red dot is the branch for T-junctions for converging, combining, diverging, dividing cases, and it's the channel for a Y-junction. Okay, channel being the combined flow. Okay, so I'm going to have a number of heat exchangers in this system, okay? So I'll just insert a few shell and tube exchangers into this system like so. Now, I can hold a shift key and multi-select components like so. And we're going to have heat transfer into the network. So we're going to add some heat into this system, and it's going to be in kilowatts for each of these 4. Now, I know 2 of them have a heat transfer of 370 kilowatts and 2 are 250 kilowatts. So I'm just going to set all 4 to 370 and then just edit those 2 into 250 kilowatts like so. So you can see 250 kilowatts of heat entering the system, 370, 250, and 370. Okay. Now, I'm going to leave default information here for the boundaries. Okay, it's 1 atmosphere pressure, it's water at 15 degrees C, and I'll just I'll insert a centrifugal pump into this network, and the red dot in this case denotes the discharge pipe for the pump. So we're pumping from left to right in this case. If this happened to be incorrect, you can swap it around by double clicking, and now you can see the red dot has repositioned, or click the grey box here as well. On the input tab, and you can see I've just reassigned it there. Now, I'm not going to model a particular manufacturer's pump. I'm going to automatically size a pump. I can choose design flow rate, or in this case, we're going to size it based on a design pressure rise. It's 2.5 bar in this case. Okay. Now, all of the pipes in this particular model, well, look, I could multi-select pipes by holding the shift key like so. So I can select all of these pipes. And now if I wanted to set all of these pipes to have a length of, 6 meters or, 2 meters or whatever it happened to be, I can do it like so. And there we have it, 2 meters, 2 meters, 2 meters, and so on. The other thing is I can select all pipes like this. Edit, select pipes. Now they're all marked off for me, and I can set them to an arbitrary length of, I'm just choosing 6 meters in this case now. So all these pipes have a length of 6 meters. Now, the default Pipe diameter is 2-inch, classification schedule 40. I'm not going to worry about that too much just at the moment. Let's calculate the model to see how it's performing here. Okay, so we've got high velocities, which we can expect because we haven't sized these pipes just yet. And the velocity is 7.2 meters per second. Okay, if I look at the input tab, the sizing model for pipes is economic velocity. I could choose design velocity, in which case I would enter my design velocity, or I could choose design pressure gradient, 360 pascals per meter in this case. I'm just going to choose economic velocity, in which case the software uses a database of sizing data. Okay, so for steel pipes, it uses energy cost, maintenance, installed cost, operating frequency per year, and so on. 365 days a year, 24 hours a day. You can adjust these values if you wish, but these are all taken from a very reliable resource, and as such, we'd recommend you retain the values. Okay. These values are used to calculate this economic velocity and exact corresponding economic size we see here. So the 52.5 millimeters we see here is the inside diameter of this 2-inch schedule 40 pipeline. Okay, I'll just show you that database. Pipes, and it's steel pipe, and it's a 2-inch line. Sorry, 2-inch line. And if we look at schedule 40, you can see it has an inside diameter of 52.5 millimeters. Okay, so that's where that value comes from. So you can see that the software is suggesting a size of 127 millimeters here. So it would be up to us to select a standard sized pipe, which is much closer to this region. Okay, now these two values or parameters here are only suggestions. They don't have any impact or effect on all the calculated operating conditions that we see here. Okay, it just helps us design an efficient system. But I'm not going to look at that just yet, because I know this system's not going to be balanced. Okay, let's just look at the flow in kilograms per second. Okay, so I'm going to right mouse click, select result units, and for flow, change that to kilograms per second. Okay, so 7 kilograms per second. Let me just change the decimal point position here, like so. Okay, 7.4 kilograms per second through the first branch, 3.9, 2.3, and 1.952. So the system's not balanced. Okay, now for this design scenario, the design temperature change across this heat exchanger might be something like 30 degrees C. So we could use Q equals MC delta T and determine what the mass flow rate required should be through each of these branch connections. Okay, so let's say we've done that. We can insert now an orifice plate into each of these lines, like so. And again, I could hold the shift key and select all of these. Now, this orifice plate came from the size change tab. So what I'll do instead is I'll just display everything in this model that falls under the size change category. And you can see we've got the 4 orifice plates. So if I select the first one, hold the shift key and select the final one, we've selected all of them on the flow sheet. And now I'm going to automatically size them like so, based on a design flow rate in kilograms per second. Now, the 370 kilowatt units, the first and third unit here, they both have a design flow rate of 2.69 kilograms per second. And the final two, or remaining two, have a design flow rate of 2.006 kilograms per second. And finally, what we'll do, just to make it a little more clear, is rotate those nodes. Okay. So now I can refresh the calculation based on having these orifice plates included. And now you can see that by defining the design flow rate, we've got 2.69 passing through this first branch now instead of the 7.45, I think it was originally. We're balancing out the flow. We've got our various tap loss values calculated for us here. And you can see the K value, but also more importantly, maybe the calculated size, 17 millimeter orifice plate, 15.2, 17.9, and 15.5. So we can see now the size of orifice plate required in order to achieve the design flow rates that we had set out as a design condition for each orifice plate in the model. Okay. Now, if we look at the messages, we've got 3 high pipe velocity warnings. Okay. So let's look at this one. Now, the warning for each of these 3 pipes is going to be much the same. Or the operating condition is going to be much the same because it's the total flow out and the total flow in this case. So 9.3 kilograms per second, and the velocity is 4.3 meters per second. And at the bottom again, 4.3 meters per second. So a little high for this system. Why do we have a high velocity warning? Well, if we look at the warnings and hints for the liquid systems, we can see that the maximum velocity setting is 4. So this just means that anything over 4 meters per second means we're going to get a high velocity warning, and anything below 0.2, we're going to get a low velocity warning message. Okay, we've got some control valve warning settings here. So if we have a control valve in the system which is operating below 20 or above 75% open, we're going to get a low or high valve position warning message. Okay, so let me just cancel that for a moment. So let's look at these values once again. We had a 2-inch line and it was suggesting a size of 99.7 millimeters, so around 4-inch, for instance. So I can now hold the shift key and select those 3 pipes, and then from the input tab, change them all to 4-inch, like so. I'll just choose schedule 40. Okay, and recalculate. And now the warning messages have disappeared for those pipelines. The velocity level is 1.14, which is a much better result. And now we just have a warning message for the T junction. Okay, and it's telling us that the idle check T relationship is outside the allowable range, or possibly outside the allowable range. Okay, now warning messages are there to help us develop an efficient system. We don't have to eliminate all warnings. Okay, we can choose to accept them based on design or engineering judgment. Okay, so the idle check pressure loss relationship, I'll just show you the definition here. The T junction is defined as idle check. You can choose Crane, Miller, or SAE. Idle check in Miller and SAE take into account reducing T's, so different sized pipe connections, whereas Crane does not. Okay, it's a much more simplified result, or correlation, I should say. So what I'll do is I'll actually change all of the T junctions to Crane. Now I just changed that one I had selected, so I'll change the others to Crane. And what you'll see is if I recalculate, those warning messages have now disappeared because that Crane method does not take into account different sized pipe connections. Now remember, we have a 2-inch line here, a 2-inch line here, like so, and we increase this to 4-inch. Okay, so the software is taking into account when using the idle check relationship the fact that we've got a different sized pipe, and extrapolating the equations to calculate the K values and losses accurately. Okay, but it's just telling us that the idle check method is valid for a certain range, and that the software is extrapolated and calculated accurately, and you might want to check the calculated branch K and straight K, or for instance swap to another method and compare the result for that method, branch K, straight K, and so on. There's further information on the limitations, etc., for these junctions in the help file and in some of the design handbooks. But you're getting an accurate result, but just be aware that correlations sometimes have a limitation. Okay, and if you're looking for a really high level of accuracy, it's worth double checking the results against the literature. Okay, so that's just a very simple example of modeling a cooling water system.